The Connecticut River has shaped New England for thousands of years, but today, this landscape is changing faster than ever. Human land use, climate-driven rainfall changes, and altered sediment transport are reshaping the river valley. In this video, we'll explore how these changes happen, why they matter, and what they reveal about the interaction between people, climate, and Earth's surface processes. Climate is one of the strongest forces shaping river systems. In the Connecticut River Valley, precipitation has become more variable, with heavier rainfall events occurring more often. Changes in atmospheric circulation and climate forcing alter where and how moisture is delivered. When rainfall intensity increases, so do erosion rates because the river has more energy to pick up sediment and reshape its channel. Heavy storms mobilize more loose sediment from hill slopes, farms, and urban areas. Over time, this reshaping creates new cut banks, erodes floodplains, and deepens river channels, all visible along stretches of the Connecticut River today.
Human activities often accelerate natural processes. Along the Connecticut River, deforestation, agriculture, and expanding urban development have exposed more loose soil to rainfall and runoff. Without vegetation to stabilize slopes, erosion increases dramatically. Urbanization makes this effect even stronger. Impermeable surface like roads and parking lots channel stormwater directly into the river, increasing flow velocity. Faster moving water carries more sediment and has more power to erode the riverbanks. Here's a simple example. In this clip, you can see how the water moves much faster over the bare soil and picks up sediment along its path. In this example, you can see how the ground covered in vegetation dramatically slows the speed of runoff and absorbs more of the groundwater. On the Connecticut River, areas cleared for farming or construction behave exactly like the bare soil model, losing sediment much faster than during rain events.
Erosion upstream affects ecosystems far downstream. As more sediment enters the Connecticut River, it travels toward the Long Island Sound, carrying nutrients, pollutants, and organic material with it. A 2021 peer-reviewed study in Frontiers in Marine Science modeled how fresh water and sediment from the river spread during flood tides. The researchers found that tidal currents rapidly mix river water and redistribute sediment. This means that changes along the river, such as increased erosion from land use changes or stronger storms, can have immediate effects on coastal ecosystems. More sediment can cloud the water, disrupt habitats, and transport pollutants into sensitive estuaries. This connection matters because it determines where nutrients, sediments, and pollutants travel. When human activities increase erosion in the river valley, these materials don't stay local. Tidal mixing can spread them widely throughout the Long Island Sound. Understanding this process helps scientists predict ecological impacts and manage sensitive coastal environments like the estuaries. As we conclude, let's revisit the three major learning objectives we explored and connect them back to what we observed in the field and in our demonstrations. First, we evaluated how shifting precipitation patterns and climate change influence erosion rates and river morphology. We learned that when rainfall becomes more intense, as climate models predict, rivers gain more energy. That extra energy increases erosion, reshapes river channels, and transports much larger amounts of sediment. We also identified three specific impacts on riverbeds. 1. Deepening of channels from scouring. 2. Widening of banks as fast-moving water undercuts the sides. And 3. Increased sediment deposition downstream where the river slows. Each of these is driven by a combination of stronger storm events, altered runoff patterns, and the river's natural response to carrying more sediment. Second, we examined how land use and human activity influence erosion, especially the difference between vegetated and non-vegetated surfaces. Vegetation stabilizes soil with root systems, slows down runoff, and absorbs rainfall, dramatically reducing erosion. In contrast, cleared land, pavement, construction zones, and agricultural fields have little to no protection, so water flows across them faster and picks up more sediment. Our real-life erosion demonstration helped visualize this. The clip with vegetation led to much lower sediment erosion, while the bare soil eroded very quickly, showing how small land use changes can greatly impact erosion rates. And finally, we looked at the downstream impacts of increased erosion and the specific byproducts that cause environmental damage. Excess sediment, cloudy water, nutrients, and pollutants all move with the flow and can smother habitats, reduce sunlight for aquatic plants, and carry contaminants into estuaries and coastal systems. These byproducts disrupt ecosystems, harm fish and shellfish populations, and even affect human communities that depend on clean water.
Our research shows that the Connecticut River is shaped by both natural climate processes and human land use. Heavier rainfall events increase the river's energy, while deforestation and urbanization feed it more sediment. Together, these forces reshape the river valley and influence ecosystems far beyond Connecticut. Understanding these interactions help us manage erosion, protect habitats, and plan for a future where climate and land use continue to change. The Connecticut River is a powerful example of how people and natural processes are always connected, and why studying earth science matters.